Welcome to this Explainer Masterclass. Today, we're tackling one of the most fascinating and ingeniously designed architectures in the world of audio processing and speech recognition, the Time Delay Neural Network, or TDNN. Our core goal today is straightforward but incredibly powerful. We're going to understand exactly how we efficiently solve what we call the temporal context problem. How do we teach a machine to understand a sound when the meaning of that sound depends heavily on stuff that happened way before it or even slightly after it? Well, let's find out. Okay, let's jump right in. At its most fundamental level, what is a TDNN? In plain English, a time delay neural network is essentially a 1D convolution over the time axis. It's used primarily as the acoustic model in hybrid automatic speech recognition systems, translating frames of audio into senone probabilities. Think of it as this brilliant tool designed to grab a really wide context of audio without completely crashing your system's memory. It looks at a small window of frames across time, and by stacking these layers together, it builds up a massive, wide view of the audio sequence. To make sure we truly master this, we're going to break things down into 3 parts. First, frame splicing and stacking. Second, efficient dilation. And finally, how the TDNN beats plain DNNs and RNNs. All right, part 1, frame splicing and stacking. Let's look at how we actually build that wide context. Before we can appreciate the solution, we've got to grasp the core problem. When we speak, sounds don't just exist in a vacuum. A sound depends on its neighbors due to things like co-articulation, where the shape of your mouth for the current vowel was actually influenced by the consonant you spoke 3 fractions of a second ago, and prosody, the overall rhythm of the speech. Because of this, our acoustic model desperately needs a wide temporal view to accurately guess the sound. To visualize how we get this, picture a literal window frame sliding horizontally across a long timeline of audio data. The exact same layer weights are sliding over the time axis. This is weight sharing in action, exactly like a 1D convolutional neural network filter sweeping across a sequence. Instead of taking in the entire audio file all at once, it just slides its little window along, processing a specific chunk at any given moment. This beautifully illustrates how the network builds its understanding from the ground up through a process called splicing, literally concatenating neighboring frames to form its input. Notice how in step 1, the very first layer splices together 5 frames. The current frame, right at 0, the 2 before it, and the 2 after it. It's a tight, local view capturing immediate acoustic patterns. But watch step 2. Layer 2 takes the output of layer 1, but it doesn't look at every single frame. It skips frames. It might just look at -2, 0, and +2. Then in step 3, layer 3 reaches out even further, maybe splicing -3, 0, and +3. By stacking these layers, we organically build this massive receptive field. The lower layers catch the local patterns, and the higher layers catch the long-range temporal structures. Which brings us to part 2, dilation for efficient computing, and the sheer power of subsampling frames. Looking at what we just discussed, you might be asking a pretty crucial question. If we keep expanding our window to see more and more of the timeline, how do we keep this massive receptive field from completely destroying our compute budget? To put that in perspective, check out this number, plus or minus 15. By the time we reach the top layer of a typical TDNN, it effectively sees a massive temporal span, roughly 15 frames into the past and 15 frames into the future. That is an incredibly wide chunk of audio context all at once. If a standard neural network tried to process a dense window of 30+ frames at every single layer, the math involved would just grind everything to a halt. The brilliant fix for this compute problem is subsampling, which is also known as dilation. In short, this means getting wide context cheaply. Instead of splicing every single adjacent offset as we move up the network, we skip frames. We dilate the splices. Remember that -3, 0, +3 pattern? That's dilation. We skip the 1s and 2s entirely. By doing this, the receptive field, the total amount of time the network is effectively aware of, grows incredibly fast, but the actual number of computations stays incredibly low. Just a few layers reach a very wide context with barely any compute. And by the way, the time delay part of the name literally refers to how each layer's view is spread out or delayed across these specific time steps. There's a line from the source material that absolutely hits the nail on the head when describing the magic of dilation. It says this method gives the wide context speech needs without the cost of a plain DNN or the sequential slowness of an RNN. It really is the best of both worlds, which perfectly sets up our final section. Part 3, beating plain DNNs and RNNs. This is the ultimate showdown. Lining these architectures up head-to-head reveals exactly why the TDNN is so dominant. Let's start with a plain deep neural network in row 1. Its temporal context is just a narrow, fixed window. If you try to widen it, you need a huge input layer or massive dense layers, and that is highly costly. Now look at the recurrent neural network, or RNN. Theoretically, it has wide context, but it computes sequentially. It has to process frame 1 to get to frame 2 to get to frame 3. That is incredibly slow, really hard to parallelize, and its memory actually fades over long distances. Finally, look at the TDNN. It achieves that wide context via stacked dilated splices, but crucially, it computes over those windows in parallel. It is highly efficient and lightning fast compared to the sequential bottleneck of an RNN. Because of this parallel, efficient design, the TDNN has what we call the streaming edge. Think about a real-world pipeline, like the famous Kaldi toolkit. Audio goes in, it's converted to acoustic features like FBANK and I-vectors for speaker adaptation, and feeds right into the TDNN. The TDNN then pushes out those senone posteriors. But here is why it's an absolute game changer for live streaming transcription. It features a bounded, specifically designed look-ahead context. Because it only looks ahead a fixed number of frames, say plus 15, frame representations become available incrementally as the audio rolls in. Contrast that with a bidirectional RNN, which literally has to wait for you to finish your entire sentence before it can process the audio backwards and forwards. The TDNN doesn't wait around. It processes in chunks, making it a total champion for real-time streaming. But hey, nothing's perfect, right? So the crucial point we have to leave you with is this. Do large weight matrices spell doom for the TDNN? Because it relies on these sliding windows, its biggest weakness is that deep versions require massive weight matrices, leading to a huge number of parameters and a really high risk of overfitting the training data. Now, the immediate fix for this was the TDNN-F, the factored TDNN, which compresses these matrices. But looking to the future, we have to ask, will models with globally learned context, like conformers that use self-attention mechanisms, just completely render the traditional TDNN obsolete for top-tier accuracy? It's a fascinating question about where machine learning architectures are heading next. Thank you so much for hanging out for this explainer. Keep learning, keep questioning, and I'll catch you next time.